Thank you very much for having me here and thank you for attending this session. Today, I'm going to talk about information design in allocation with costly verification. This is a joint work with Yi Chunchen from National University of Singapore and Xiang Chenyang from Hunan University. I myself is from Shanghai University of Finance and Economics. As you can see from the title, this paper is a combination of two topics, information design and the allocation with costly verification. Okay, I will explain the terms one by one. So first, we consider the allocation problems in the style of Benport, Steichel, and Lippmann. Here are some examples to illustrate the allocation problems. First, an economics school may consider whether to recruit a PhD student from its undergraduate students. Second, a venture capital firm may consider whether to fund a startup firm from a set of competing ones. And third, a central government may consider whether to build a new hospital in one of several towns after a disaster, like an earthquake. And the fourth example we are quite familiar with, a research funding agency may consider whether to support one of several competing researchers. In those kind of allocation problems, we have a principal who has an object to be allocated to one or more agents. And there are three key features. First, agents have private information. And second, there's no monetary transfer. Third, costly verification is available. That means if the principal pays a cost, the principal can learn the agent's private information. Okay? And we're going to enrich this allocation problem by adding some information designer into it. Okay? So who may serve as the information designer in the allocation problems? Like in the previous examples, in the first one, the undergraduate student's thesis supervisor may be the information designer. So this may be a third party. And in the second example, some rating firm may be the information designer. Okay. And in the third example, the town council may be the information designer. And in the last one, some external grant referee may be the information designer. So with an information designer, the three key features now become the following ones. First, the agents have prior information, which is a signal learned from the information designer. Second, this is the same as before, no monetary transfer. Third, when the principal pays a cost, the principal can learn any agent's signal. Okay. So this is the story. And now let me introduce the model. We consider a single agent model first, and the extensions to the multiple agent case will be discussed in the end if we have some time. Okay. First of all, some preliminaries. We denote agent's type by small t, and the type follows the distribution capital F. The support of F is an interval. Okay. For the agent's utility is simply the probability P of getting the good. For the principal has a reservation value R. And if the principal allocates the good to the agent, then the principal gets an allocation payoff of T minus R. This is a net value. Now about the information, we assume that neither the principal nor the agent knows the distribution F or its realization T. And we also assume that the information designer knows the underlying distribution F, but not the realization T. Okay. So the principal and the agent may receive information from the information designer. The agent learns a private signal S about the type T, and the principal learns the distribution G of the signal S. Usually, the distribution G is designed through some joint distribution of the signal and the type. For example, H of T and S. And there are some consistency requirements. The marginal distribution of the joint distribution on T should be the same as the underlying distribution F on T. Okay, and the marginal distribution on S is the same as the designed distribution G. Okay, so actually we can simplify the information design problem according to the results of Rosland, Zentis, and of course Blackwell. So what the information designer can choose? The information designer can choose from the set of marginal distributions of unbiased signals. We denote it by GF, that set. Okay? And that set is the same as the set of mean preserving contractions of the underlying distribution F. So the signal distribution to be designed is dominated by the underlying distribution F in the second order sense. Okay? The agent lends the private signal S about the type T through the signal distribution G. And the principal lends the distribution G. Okay. And of course, we should have the costly verification part in mind. If the principal pays a cost C, the principal lends the realized signal S. And the allocation payoff to the principal actually depends on whether the principal checks the agent. If the principal does not check the agent, then the allocation payoff is S minus R. If the principal checks the agent, then the allocation payoff is S minus C minus R. Here, I want to say that calculating the allocation payoff using the signal S is actually the same as using the tab T because we care about expected values and the signal S is unbiased. Okay. So here is the timeline. The information designer designs the signal distribution G, and according to the distribution G, the principal designs a mechanism. Okay. Let's consider the mechanism design problem. Given the designed signal distribution G, and let's imagine that we are considering a direct mechanism. So in a direct mechanism, the agent reports a signal S to the principal, and with the reported signal, the principal may or may not check the agent. Q of S is the probability of being checked. And we use P and C of S to denote the assignment probability conditional on not being checked. So P not being checked. Okay. When the agent is checked, there are two possible checking outcomes: truth telling or lying. According to the result of BDL, when the agent is checked and found truth telling, the conditional assignment probability should be 1. So Q of S is actually the probability of being checked and allocated the good. Okay? And when the agent is checked and found lying, the conditional assignment probability should be 0 to provide the incentive for the agent to tell the truth. Okay? We use P of S, this new notation, to denote the total assignment probability, which consists of 2 parts. The first part is the assignment probability from being checked. The second part is the assignment probability from not being checked. BDL shows a revelation principle, and with the revelation principle and the simplification we just mentioned, we can focus on the simplified direct mechanism. The simplified direct mechanism consists of 2 rules, the checking rule and the allocation rule. So Q assigns for each reported signal a checking probability, and the P function assigns for each reported signal a total allocation probability. Okay, so there's a natural restriction. P of S should be greater than Q of S for any signal S. Okay, and this restriction is just from the definition of the P notation we just introduced. Now, what's the principal's mechanism design problem? The principal chooses the 2 functions P and Q to maximize the expected payoff of allocation. And the expectation is taken using the distribution G. Okay, look at the objective function. The first part is the allocation payoff. And the second part is the checking cost paid. There are a bunch of constraints. The first two constraints are quite simple. They just say that both the P and the Q values are probabilities. And the third constraint is the one we just mentioned. And the last constraint is the incentive compatibility constraint, which simply says that truth telling is better than lying. If the agent reports the true signal S, then the total assignment probability is P of S. And the right-hand side, if the agent misreports some other signal S prime, the agent can get the good only if the agent is not checked. So it's P minus Q, okay? Now, we come to the information designer's objectives. The information designer may have different objectives. So we consider three information design problems. First, agent optimal information design. In this problem, the information designer chooses a signal distribution G to maximize the agent's utility, which is the probability of getting the good. And when calculating the agent's utility, the assignment probability P should be from some optimal mechanism designed by the principal. Okay. And the second problem is the principal worst information design problem. In this case, the designer chooses a signal distribution G to minimize the principals, maximize the payoff from the mechanism design problem. So at the first glance, the motivation of this principal worst information design problem is unclear, but we will use the result of this principal worst information design problem to study the related robust mechanism design problem. So one of them is the min-max problem, and the other is the max-min problem. And the third information design problem we are going to consider is the principal optimal information design. So the designer chooses a signal distribution G to maximize the principal's payoff from the optimal mechanism. So three information design problems to be solved. Here is an overview of the results. So first of all, we can fully characterize the set of optimal information in all three information design problems. Okay. Here are some concrete examples of optimal information. For the agent optimal one solution actually pulls information above a cutoff signal and fully reveals information below that cutoff. Okay. For the second one, principal worst information design, making a signal distribution G the least informative is principal worst. And for the last problem, making the signal distribution G the most informative is principal optimal. Okay, those are just examples of the solutions. We can fully characterize the set of solutions. And given the characterizations, we have two observations, which are the third and the second bullet points. Okay, the first observation, we found that any agent optimal information is principal worst, but not the converse. And the other observation is about robust mechanism design. After we solve the principal worst information design problem, the principal's payoff under the principal worst information actually serves as an upper bound for the principal's payoff under robust mechanisms. And we found that there exists a robust mechanism such that the principal's payoff under this robust mechanism achieves the upper bound, in which case that robust mechanism must be an optimal robust mechanism. So the principal worst information design problem helps us to solve the optimal robust mechanism design problem. Okay. So far, the results are all about the single agent case. And many of our results actually extend to the multiple agent case, but not all. So here is the literature review. And obviously, our paper is related to three streams of literature. First, allocation with causality verification. And second, information design. And third, robust mechanism design.